Alrighty, so now we're going to use conservation of energy to solve some physics problems. So the first example I want to show you is this idea of a block sliding down a frictionless slope. And I want to know how fast it's going to be going at the bottom. And we'll assume that at the top it was not moving when it was at a height of 30 meters. And then it slides down this incline at an angle of 20 degrees. So the way that we used to do this with forces is we would draw our gravitational force, or mg, and our normal force, n, and we would find our gravitational force x and y components. So in the in the y direction it would be mg cosine theta, and in the x direction it would be mg sine theta. And then I would be able to just cross out this gravitational force. So in other words, my gravitational force in the x direction is this mg sine of 20 degrees. So I know that the sum of all my forces, whatever they are, is equal to ma. And so in this case, I have the sum of the forces in the x direction is just going to be fgx, which is equal to mass times acceleration in that x direction. So I substituted in the mg sine 20 for fgx, and then I divided both sides by m, and I get g sine 20 is equal to a, which gives me an acceleration of 3.35 meters per second squared. All right, so now I have my acceleration. Now I just need to find my velocity at the bottom of this hill. So I need to find the distance to the bottom of the hill because I'm starting here and ending here. I need to find that distance. I know the height of the hill. So to calculate this distance, I'm going to use sine, which is opposite over hypotenuse. So sine of this angle is my opposite, or 30 over hypotenuse, which is my d. I plug in the numbers, move them around, so I multiply d onto both sides to get it out of the denominator. I divide both sides by sine of 20 degrees to get that to cancel out, and I'm left with d is equal to 30 divided by sine of 20, which gives me 87.7 meters. All right, so now I have acceleration and I have distance. So knowing this, I'm going to use this kinematic equation. So my final velocity squared is equal to my starting velocity squared plus 2 times my acceleration times my change in position or distance that I've traveled. On your equation sheet, this is delta x. I plug in the numbers from the problem, and I get v squared is equal to 588. Take the square root of both sides, and I get a velocity of 24.25. So this was fairly complicated. I had to use net force equations to get an acceleration. I had to use trig to get the distance traveled, and then I needed to use kinematic equations to solve for my velocity. There must be an easier way. And in fact, there is an easier way. And that is using energy. So at the top, I have gravitational potential energy. And at the bottom, my height is going to be basically 0. So when you think about GPE, it's m times g times your height. And if your height is 0, then my GPE will be 0 here. So this is the bar chart that I end up with. I'll have kinetic energy is 0 in the beginning because it's not moving at the top. And then at the bottom, I have all kinetic energy because my height is going to be 0. If I add the left side together, 0 plus GPE plus 0 is going to be equal to my kinetic energy plus 0 plus 0. So I can say that my gravitational potential energy in the beginning is going to be equal to my kinetic energy at the bottom of the hill. All right, so my gravitational potential energy at the top is going to be equal to my kinetic energy at the bottom. So gravitational potential energy is mgh, and kinetic energy is 1/2 times my mass times my velocity squared. And then I'm going to divide both sides by m because they all have m. And I get gh is equal to 1/2 v squared. And then the next thing I want to do is move that 1/2 to the other side so I can multiply both sides by 2. And then when I do that, I'm going to be left with v squared on the right-hand side, so I'll square root both sides. And I get, so 2 times 9.8 times 30, and then all of that square rooted, and I get 24.25, which is the exact same answer that I got when I did it the harder way. But this way took me 1 slide, and the other one took me 3 slides to do. So you see how this one, this way is much easier when you're able to use energy. So, thinking about conservation of energy, I have another example for you. A young girl wishes to select one of the frictionless playground slides illustrated below to give her the greatest possible speed when she reaches the bottom of the slide. So, thinking about the different shapes and how she's starting at the same height and ending at the same height for all 4 of them, um, which one is going to be the best, or does it not matter? So my hint is, which one will she have more kinetic energy at the bottom? The answer is it'll be the same because she starts with the same gravitational potential energy for each one of these. Therefore, she will end with the same kinetic energy and therefore will be traveling with the same velocity at the bottom. This, of course, only works when it's frictionless. That's why I've bolded the word frictionless. So, with no friction, the distance traveled does not matter when something falls from a given height. It always ends up going the same speed at the bottom, which is interesting because that also means that you could assume that the object is starting at this height and just falling down to figure out the velocity at the bottom. So here's another example, but this is kind of the opposite. So here I want you to think about work and energy, regardless of which cart you look at, they are all going to have the same amount of work done to get to the top. Now, the forces are going to be different. This one on the left, you have a smaller force, but you're going to have to push it a larger distance to get it to the top, to the same height. Whereas the one on the right, you do not need to push it as far, so your distance is less, but your force is more. And so that aligns with this idea of your change in energy or your amount of work done is going to be the same.